In this video, I'm going to cover Dalton's law and Avogadro's law. So in this first example, it says a hyperbaric chamber can be used for medical uses, carbon monoxide poisoning, and decompression illness, which is the bends, amongst others, by providing a higher than normal pressure and oxygen content. What partial pressure of oxygen in atmospheres is supplied to a patient if the total pressure is 615,000 pascals and the gaseous mixture is 55% oxygen gas. All right, so there's a couple things given here. One is that it gives me the pressure in pascals, and I have to solve for it in atmospheres. And it gives me the total pressure, and it's asking me for partial. So before you start the problem, think about what you should get as an answer sheet. You end up with a number higher than 615,000 or lower. So 615,000 pascals is the total pressure. I should end up with a smaller number as a partial pressure for oxygen. Now, since we need it in atmospheres, I'm going to convert the 615,000 pascals into atmospheres. So conversions, just like the way we've always done it. Whatever units you're given go on the bottom, and the conversion factor is there's 101,325 pascals in 1 atmosphere. When you do the math for this, you get an answer of 6.07 atmospheres. Since 615,000, there's no decimal point here. So that is 3 significant digits, so we need our answer in 3 significant digits. So we get 6.07. So now what we could do is take that 6.07 atmospheres, multiply it by 55%, but we have to change that 55% into a decimal. And when we do that, since 55% is 2 decimal places, we get our answer to do 2 decimal places. You could, if you wanted to, you could have multiplied the 0.55 by that original pressure of 615,000 pascals. You get an answer in pascals, and then you can convert that to atmospheres using this same conversion factor. You would get the same answer, 3.3 atmospheres. It doesn't really matter which order you do that in. All right, the next problem continues on with that hyperbaric chamber scenario. If the partial pressure of oxygen is 975 millimeters of mercury, and that makes up 35.0% of the total pressure, what is the total pressure in the chamber? All right, think about what it's asking you now. It wants to know total pressure. Total pressure should be larger than partial pressure. So think about that before you actually start plugging numbers into the calculator. If you get total pressure, or to get total pressure, you would take that partial pressure, 975 millimeters of mercury, divided by the 0.350, right? Since this is 3 significant digits, we want to turn that percent into a decimal. It becomes 0.350, and we end up, when it's rounded off, to 2,790 millimeters of mercury. The 975 is 3 significant digits. The 0.350 is 3 significant digits. So I write my answer with 3 significant digits, 2,790 millimeters of mercury. Before you do a problem with percentages, think about whether you should get a number bigger or smaller. A common mistake with a problem like this is people are just used to taking the percent or the pressure and just multiplying it by the percent. If you do that, you end up with a smaller number for total pressure, which does not make sense. So think about it for a minute before you actually start the problem. Okay, another type of Dalton's law problem. The pressure of a mixture of nitrogen, carbon dioxide, and oxygen is 150 kilopascals. What is the partial pressure of oxygen if the partial pressures of the nitrogen and carbon dioxide are 100 kilopascals and 24 kilopascals respectively? So we have 3 different gases in here, and it tells me the total pressure is 150 kilopascals. So what happens is all of the gases, the pressures of all the gases should add up to that total pressure. So what happens here is we have total pressure should be the pressure from the nitrogen added to the pressure of the CO2 added to the pressure of the oxygen. We know the total pressure. That's 150, and I'm leaving out the decimal point, kilopascals, because no decimal points shown here. So just kind of pay attention to that. It's not going to make a huge difference in this problem, because all we're going to be doing is adding or subtracting. But if you were multiplying or dividing, that would change the number of significant digits. All right, the partial pressure of nitrogen is given as 100 kilopascals. We are solving for O2. It also gives us carbon dioxide. That is 24 kilopascals. And we want to solve for partial pressure of oxygen. So all you have to do is subtract. When you look at these questions or these numbers that are given here, when you subtract, you go by the least number of decimal places. And since these are all whole numbers, our answer should end up being a whole number. So pressure, the partial pressure of O2 should just end up being 26 kilopascals. Dalton's law just says the partial pressures of the individual gases add up to a total pressure. So that one's pretty straightforward. Just pay attention that when you add or subtract, you go by decimal places and not significant digits. All right, this problem goes along, right now I'm going to say this goes along with Avogadro's law. There's actually another law that we haven't done yet that this will go with, the ideal gas law, but we could solve this with Avogadro's law. So we have enough information right now. It's saying 50 grams of nitrogen gas has a volume of blank liters at STP. And STP, our key thing here. If it didn't say at STP, you would not be able to use Avogadro's law. Start off with the 50 grams of nitrogen gas. The only thing we could really do with this is convert it into moles, because Avogadro's law says that at STP, 1 mole of a gas is equal to 22.4 liters, and we need to use that information to solve for this. So what we have to do is convert the nitrogen, that 50 grams of nitrogen, into moles. It's always 1 mole, and you get the grams off the periodic table. Now this is a common mistake people make if you're going too fast. People look up nitrogen and they see that it's 14.0. Remember, there is a subscript here. You have to double it. 28.0 grams. So now grams of N2 will cancel out. What we have to do now is use Avogadro's law. 1 mole of a gas at STP is 22.4 liters of that gas, regardless of the molar mass. So you do the math for this, matching the significant digits to the number of significant digits in the problem. You get 40 liters of N2. So